Okay, 10:29. Landon, tomorrow.
I know I give
Are you going to get it back?
Well, it's ready right now, so Mom might give it back tonight.
I hope so, because I'm tired of loaning my truck out and getting my truck thrashed. Okay, here we go. Objective. Today what we do is we're going to talk about radians and arcs. Okay? So, Ben, can I borrow that back real quick, please? Okay. And so, radians are angles. Okay, I'll say it again. Let's write that down. Okay, phones away. Write this down, okay? Star. Radians are angles. And there's more. Radians are angles, okay? But so are degrees. Radians are angles that relate to arc length. Okay, radians are angles that relate to the arc length. It's totally different than degrees, because degrees do not have any connection to arc length unless you use the circumference formula, right? And then what do you know? Think about circumference. Circumference is diameter times pi. Times pi. So all of a sudden, once you make that conversion, you're starting to get into radians anyway, right? So, we talked yesterday, just very briefly, that if you had in a circle, if you had a radius of 1, and if the arc length was also 1, then you get an angle called theta. And that angle is 1 radian. That's what, now it's about 57 degrees, but as far as a radian, so if you have an angle whose radius is 1 and the arc length is 1, that is what we consider as 1 radian. So we have that theta here is equal to 1 radian. So the angle is the same measure as the arc length. Of course, we know if you go to half circle, go all the way half circle, you got a 3.14 of these. And that's where you start to get your pi's in there, okay? Now, if you have the unit circle, conversions are easy. Remember, there's two ways to describe angles. Two. One is in degrees, but remember, degrees for dummies. But we know that 120 degrees has a radian angle called 2 pi thirds, okay? Same angle, different name. Here's the cool part. This 2 pi thirds, the arc length from here to here, if the radius is 1, is exactly also 2 pi thirds. So the angle is going to be the same as the arc length, okay? Well, something easy. This is pi, right? This is pi. The angle is pi, but so is the arc length, right? This is pi halves. And then the arc length is also pi halves, right? This is 90, but this is not 90. This is not 90. It's 90 degrees, but not a 90 length. Are you with me? It's not a 90 length at all, okay? So, if I want to convert, the easy ones are easy. So for instance, I want to convert 210, it's 7 pi 6. Just get it off the unit circle. If I want to convert 7 pi fourths from radians to degrees, that's easy, it's 315, right? But if it's an angle that's not on the circle, because, I mean, how many of these do I want to draw? Well, I drew all the special ones. I drew all these unique ones that come from the 45, 45, 90 triangle and the 30, 60, but there's other angles, 50-degree angles, 40-degree angles, right? 36-degree angles. There's no way we're going to put all of those up there, so we need a conversion to be able to convert all the other angles. So my conversion is this, okay? Here's my conversions. If I want to convert degrees to radians, okay, here's my formula, okay? So, example 1, 140 degrees. We're just going to use the formula. So we're going to say my radian, R equals, just use the formula, R equals my 140 goes in for D, 140 over 180 pi. Now, if we can keep things in terms of pi, it's more accurate. Because pi is 3.14 blah, 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 blah. But if we can keep it as a pi, it's more accurate. So if we reduce, that would be reduced to 2/9. Now, there's a cool button in your calculator for reducing, right? I'll show you real quickly. So if you go to 140 divided by 180, okay? And if I want to reduce that fraction, just reduce, I go to Math, highlight Fraction, and my calculus is going to do the reducing for me. Isn't this slick? Boom.
Can you show us again? I'm sorry.
Yep. Okay, so if I want to reduce 140, forget about the pi, not the pi, but if I want to reduce this fraction, 140 out of 180, we could say, well, they both divide by 10 and they both divide by 2, and I could get 7/9. I could do that in my head. But if not, I go to Math, highlight fraction, and it will reduce my fraction for me. So 140 over 180 is 7/9 pi. Isn't that nice? So it becomes just 7/9 pi. So on the unit circle, it's right around here somewhere, right? 7/9 pi. Okay. Now, we can do the same thing if we want to convert to degrees. So if I got a 5 pi 12, so 5 pi 12, let's see, it's a little bit less than half a pi, so it's somewhere around here. The answer is going to be probably about an 80 some odd degree angle, maybe. So the conversion is to convert it back to degrees. We're just going to simply take and go, our degree is equal to 180 over pi times my 5 pi 12. Okay? So all I did is I put my radian in for the r into the formula. So I go 180 over pi times my radian, right? Let's cancel the pi's, and we'll just go 5 times 180 divided by 12. Okay, that's all I'm going to do. I'm going to go 5, clear. I'm going to go 180 times 5 divided by 12, and I get an answer of about 75. I knew it was close to that. So I get a 75 degree angle. So on my unit circle, 5 pi 12 is right around here somewhere, 75 degrees, okay? Kind of makes sense, right? So they're both angles, one's in degrees, one's in radians, that's all. Now, arc length. So to do an arc length, it's equal to S is the symbol for arc length, equals r theta. Now, theta's got to be in radians because the whole connection between angles and arc length is in terms of radians, okay? So if I take a look at example 3 and I want to find this arc length, so the arc length is from here to here, A, B. So if I were to take a piece of string, roll it across the arc, take it off and straighten it out, say how long is this thing? Well, it's kind of hard to do, right? It's kind of hard to do. However, we can just use the formula. First of all, before we do this formula, theta is 100 degrees, right? But what we need is we need this thing in terms of radians, okay? So the first thing, in order to use this formula, is I'm going to convert my theta into radians, okay? So first, let's convert 100 degrees to radians. All right, I can do that. That's just going to be 100 over 180 pi, okay? And that reduces to, you can draw it on a calculator, but it reduces to 5/9, right? 5/9 pi, okay? So that's my angle. So if I'm going to use my formula, I go, okay, I can do this. I can go S equals 5/9 pi times my radius, which is 5. So I'm going to get an answer of S equals 25/9 pi centimeters. Now, sometimes we need a decimal answer. I mean, honestly, if I already go into Marston's, tell the guys at Marston's that I need a tow board for track that was 25/9 pi, and they'd look at me like I was an idiot, right?
Why?
Right? Because they go, what? Oh, why? 29 pi? What are you talking about, right? So they can say, how many inches? Well, first of all, centimeters, that's in the bottom too, right? So sometimes you need the decimal answer, so I'm just going to use my calculator and get a decimal answer so that the guys and gals at Marston's can give me an answer. So if I go 5 pi divided by 9, oops, sorry, 25 pi divided by 9, I get an answer of about 8.72 centimeters, okay? So about 8.72 centimeters is going to be that arc length, okay? Now, area of a sector. Area of a sector is like, okay, how much area is in the wedge, okay? What's the area of the sector? Well, that's not too bad because I've got a formula. So K is the area, 1/2 theta r squared, okay? But theta's in radians, right? Okay, so if we want the area of this sector, and I think that's what example 4 says. No, it doesn't. Well, let's do it anyway. It's in a hurry. So I want to find, let's find the area of this. That's pretty easy. The area, we already know what theta is, don't we? Theta is 5 pi ninths. So we're going to go 1/2 5 ninths pi times the radius squared, which is times 5 squared. And again, I'm just going to use a calculator. 125 over 18, or I'm just going to use a calculator and get a decimal answer. So I'll just simply go, let's see, 0.5 times 5 pi times 5 squared divided by 9, and I get an answer of about 21.82 centimeters squared, okay, for area. How am I doing? Am I going too fast? Am I good? Am I going too fast?
Good.
Good? Okay. Now, ready to turn the page?
Yes.
All right. Angular speed. So, angular speed, think about this. You got a bicycle. You flip it upside down because you don't want to work on it, right? It's upside down. You spin the wheel. How fast is the wheel going? Well, the bike is not moving, right? It's upside down. So the bike's not moving, but the wheel's spinning, right? So that's angular speed. How fast is the angle rotating, okay? So angular speed is going to be W, which is over theta. Now theta is going to be the total angles, okay? So for example, theta is going to be my total angle. So for instance, if I spin it and it goes around 2 full revolutions, it's gone 720 degrees, right? Does that make sense? Possibly in a second. 1001, okay? So its angular speed would be 720 degrees in 1 second, right? But theta's got to be in radians because when we start to try and put it in a linear speed, that's when we tip the bicycle over and go. It's linear with me. That's going to be going forward. It's a linear speed. So the angular speed is going to be the total angle over time. Well, that's not too bad. So we've got a bicycle, a wheel of 18-inch diameter. And we don't need this yet because we're not going to put the bike on the ground and run it, right? So regardless of where the bike is, the angle, regardless of where you are, travels the same. Think about the Earth. You know, the Earth is spinning around, right? And within 24 hours, it's going to go around. If you're at the equator, this makes sense, you're moving a lot faster around the Earth than somebody who's at the North Pole. Does that make sense? However, you're both going around in one day. Isn't that crazy? Isn't that crazy? Think about it. If you were standing way up in Norway, you're still going around the Earth in 24 hours, same as somebody at the equator. But somebody at the equator is going a lot faster.
Wait a minute. But you're still going the same amount around?
Yep, and that's the difference between angular speed and linear speed. Because angular speed is going to say everybody's going around the Earth in one day, right? But if you're at the equator, you're spinning a lot faster. And that's your linear speed. Okay? So your rotation is 24 hours in one day, regardless of where you're at in the Earth. Think about it, right? If you're standing at the North Pole, can you visualize this? You're going to go from here to here in 24 hours, right?
But that's at the
Very,
core,
yeah,
right?
that's very, very top of the North Pole, right? You're going to stand at the North Pole, you're going to spin. It's going to take you 24 hours to do this. Crazy, you're barely moving at all, right? Now think about an airplane. And you guys, most of you have been on an airplane, I assume, right? Think about an airplane. If you're going to fly, and I know a lot of you guys have flown to Hawaii or whatever, right? That airplane's moving really fast, and you're still not keeping up with the sun, right? So you have, so at the equator, man, you got to be, because you got to be moving all of that distance in 24 hours. You got to be moving pretty fast, don't you? So So there's a difference between angular speed. Angular speed means even right here, right? Going around, and so it's the angle versus the linear speed. So the 18 inches is not relevant until we get to here, okay? So a bicycle wheel of 18 inches and diameter spins 20 times in 3 seconds. So it's going to go 20 times. And then what's its angle? So it goes 20 times all the way around. What's the angle?
7,200.
Right, for 20, but in
7,000
radians, because we have to do it in radians, yes. We're not going to do it in degrees. We're going to take 20 times 2 pi. All right, go back to your unit circle, right?
Because that's the full,
That's a full spin, isn't it? 2 pi. Does that make sense?
okay.
We're going to do 20 of those in 3 seconds. I mean, we're cruising along, right? So we're going to go 40 pi radians in 3 seconds. So that's how fast my tire's spinning, okay? Which way?
Is that same? Oh, okay.
So if I just, I could divide that if I want to. I'll go 40 divided by 3 times pi gives me about 41.88, 41.8989 radians per second, okay? So 3.14 is a half circle, 6.28 is a full circle. So I'm going to do 41, or I'm going to basically do 40 and 20 in 3 seconds. Okay, so now that's how fast the tire's spinning. Okay, that's how fast the tire's spinning. Flip it back upside and get on it. Now we're going to move forward, aren't we?
It'll go faster.
Well, what's going to happen is this.
What?
Now we're going to get on the bike and we're going to go forward.
Yeah.
That's a linear speed because
So
the
it's
bike's going to go
completely
forward. It is. So the bike's still going to be spinning, right? But what affects this is the size of the wheel. Little itty bitty wheel. If we spin really fast, we're not going to go very fast, are we? Humongous wheel, spinning that fast, we're going to fly, right? So how big is the wheel? Well, the wheel is 18-inch diameter, which makes it a 9-inch radius, okay? So in this case, we've got a 9-inch radius. So our radius is equal to 9 inches, okay? And S is like the total arc length. So S is equal to R theta, right? That's what we learned. S is my arc length. I already know my angle. My angle is going to be this 40 pi thirds, right? It's going to go that many radians in 1 second, right? And then that's going to be times my radius, which is 9, okay? So then if I multiply that out, let's see, I've got 40 pi. Let's just take my answer clear. Take my answer, divide it, or multiply my answer by 9. Hold on. 40 times pi times 9 divided by 3, and I get an answer of about, almost about 377. So I get about 377, and that's in terms of what, though? What's my speed? In inches per second, all right? So come on, somebody ask. I'm on a bicycle. Somebody ask. I'm going 377 inches per second.
What's the speed?
In what?
How do we convert it?
How do we convert to what?
Miles per hour.
Miles per hour, right?
Centimeters.
No, miles per hour. No, we can do that. That's conversion you guys know, okay? So you've done this in science. At least I hope you've done this in science, right? So first, let's convert the seconds to hours. That's the easy one, right? So I'm going to take my little 377 inches per second. How many seconds are in a minute?
60.
And you got to cancel words, right? So 60 seconds.
It's gonna go above.
Yes. For 1 minute. Remember, you got to cancel words. That's how it always works, right? Now I need to get hours, so there's 60 minutes in 1 hour. So where should I put the 60 minutes?
On top.
Because I want the minutes cancel, right? 60 minutes per hour. Okay, awesome. Now, I got to go from inches to miles. So first, there's 12 inches in a foot, and there's 5,280 feet to the mile. Okay, did you hear that? I know these numbers, okay? 5,280 feet to 1 mile. Okay, I know, being a math nerd all my life.
Wait.
Not meters, because it's 1,600 meters, which is 1,760 yards, right? So it's the conversion, just because a meter and a yard are slight, about 3 inches difference, okay? All right, I'm glad you're thinking, Landon. So let's change this. So I got to cancel my inches. There's 12 inches in 1 foot, so 1 foot is equal to 12 inches, right? So my inches cancel. In fact, we could even do a little canceling because it's kind of fun to cancel, right? I can cancel seconds with seconds. I can cancel minutes with minutes, right? I like doing the cancel. It's kind of fun. Now I can cancel inches with inches, right? Now how many feet are in a mile? Well, I just told you there's 5,000. Okay, so there's 5,280 feet in 1 mile, right? And then my feet cancel, And what are my units? What are my words? My words are miles per hour, and that's what we're looking for, right? So now I'm just going to multiply, right? See how that works? Did you guys do this in science ever? I'm hoping you did. Yep, I'm hoping you did this in science. So I'm going to go 377 times 60 times 60. Enter, divided by my 12 times my 5,280, and I can answer about 21.4 miles per hour. That's not a bad speed on a bicycle, right? Okay, I'm going to stop recording, and please ask, okay?